Gravity. It's the force we experience every moment of our lives, yet rarely stop to ponder. We take it for granted as it is always there, silently working in the background. It keeps our feet planted firmly on the ground, prevents us from floating away into the vastness of space, and dictates the motion of celestial objects billions of times more massive than our planet. From the smallest pebble to the largest star, gravity is the invisible hand that guides their paths. But what exactly is gravity? How does it work, and why is it so crucial to our existence? In simple terms, gravity is an attractive force that exists between any two objects with mass. This means that every object in the universe, no matter how small, exerts a gravitational pull on every other object. Every single atom in your body is pulling on every other atom in the universe, and they are pulling right back. This mutual attraction is what keeps us grounded and what holds the universe together. The more massive an object, the stronger its gravitational pull. For instance, Jupiter, the largest planet in our solar system, has a gravitational force much stronger than that of Earth. This force is what determines the weight of objects, which is why you weigh more on Earth than you would on the Moon, where gravity is weaker. Gravity dictates the trajectory of planets around stars, ensuring that they follow predictable paths. Without gravity, planets would drift aimlessly through space, and the delicate balance of our solar system would be lost, and even influences the flow of time itself. According to Einstein's theory of general relativity, massive objects like stars and planets warp the fabric of space-time, causing time to slow down near them. Without gravity, our universe would be a vastly different place, a chaotic soup of particles scattered across the cosmos. There would be no stars, no planets, and no life as we know it. Gravity is a fundamental force of nature, one of the four fundamental interactions that govern the behavior of the universe. The other three are electromagnetism, the strong nuclear force, and the weak nuclear force, an invisible tether connecting every bit of matter in the universe. This interconnectedness is what gives structure to the cosmos, from the smallest particles to the largest galaxies. It is a force that shapes the cosmos, influencing the formation of stars, the orbits of planets, and the structure of galaxies. From the smallest particles to the largest structures, gravity is the glue that holds the universe together, a force that is both familiar and profoundly mysterious. Despite centuries of study, we are still uncovering the secrets of gravity, and it continues to inspire wonder and curiosity in scientists and laypeople alike. Imagine for a moment that you're standing at the edge of a diving board, looking down at the shimmering water below. You take a deep breath, take the plunge, and for a few exhilarating seconds, you experience the sensation of weightlessness, of being completely free from the pull of gravity. This, my friends, is freefall. In the realm of physics, freefall describes the motion of an object when the only force acting upon it is gravity. In this state, objects regardless of their mass fall at the same rate, accelerating towards the center of the Earth. This means that a feather and a bowling ball, if dropped from the same height in a vacuum, would plummet to the ground simultaneously. Of course, in the real world, factors like air resistance complicate things, causing objects with different shapes and sizes to fall at different rates. But the fundamental principle remains: in the absence of other forces, gravity treats all objects equally, pulling them towards the Earth with the same unwavering force. We've all felt it, the relentless pull of gravity tugging us back down to Earth after we jump, the force that dictates the arc of a basketball as it soars towards the hoop. This constant pull is quantified by a value known as the acceleration due to gravity, denoted by the letter g. On the surface of Earth, g has an approximate value of 9.8 meters per second squared. This means that for every second an object is in free fall, its velocity increases by 9.8 meters per second. So a ball dropped from a rooftop wouldn't fall at a constant speed, it would accelerate continuously, getting faster and faster until it hits the ground. This constant acceleration due to gravity is the reason why a ball thrown upwards eventually slows down, stops momentarily at its highest point, and then begins its descent back to Earth. It's a testament to the relentless, ever-present nature of gravity's influence on our planet. Section 4. Mass versus weight, two sides of the same coin. We often use the terms mass and weight interchangeably, but in the realm of physics, they represent distinct concepts. Understanding the difference between these two is fundamental to grasping the basics of physics and how our universe operates. Mass, measured in kilograms, is an intrinsic property of an object, a measure of its resistance to acceleration. It is essentially the amount of matter contained within an object. This property remains constant no matter where the object is located in the universe. It's the amount of stuff an object is made of, regardless of where it is in the universe. Whether you're on Earth, Mars, or floating in the vacuum of space, your mass does not change. This is because mass is not influenced by external factors like gravity or location. Weight, on the other hand, is a force measured in newtons, and it depends on both the object's mass and the strength of the gravitational field it's in. Weight is the force exerted on an object due to gravity. This means that weight can vary depending on where you are in the universe. It's the force exerted on an object by gravity. For example, the weight of an apple on Earth is the force with which gravity pulls it towards the ground. This force is what we commonly refer to as weight in our daily lives. So, while your mass remains constant, your weight would change dramatically if you were to travel to a different planet with a different gravitational pull. This is because the gravitational force varies from one celestial body to another. For instance, on the Moon, where the gravitational pull is about 1/6 that of Earth's, your weight would be significantly less. This reduced gravity means that the force pulling you towards the Moon's surface is much weaker than on Earth. You would feel lighter, be able to jump higher, and objects would take longer to fall to the ground. This is why astronauts on the Moon appear to move in slow motion and can perform impressive jumps with ease. This difference highlights the crucial distinction between mass, an inherent property, and weight, a consequence of gravity's pull. Understanding this distinction is essential for studying physics and comprehending how different forces interact in our universe. It also helps us appreciate the unique conditions on other planets and celestial bodies, and how they would affect our daily lives if we were to visit them. To further illustrate, consider the gravitational pull on other planets. On Jupiter, where gravity is much stronger than on Earth, you would weigh more despite having the same mass. Conversely, on Mars, with its weaker gravitational pull, you would weigh less. This variability in weight due to different gravitational forces is a fascinating aspect of our universe. In summary, while mass and weight are related, they are not the same. Mass is a measure of the amount of matter in an object and remains constant, regardless of location. Weight is the force exerted by gravity on that mass, and can change depending on the gravitational field strength. This fundamental understanding is crucial for anyone studying physics or interested in the workings of our universe. By grasping the difference between mass and weight, we can better understand the principles of physics that govern our world and beyond. This knowledge not only enhances our comprehension of everyday phenomena, but also prepares us for exploring the vast and varied environments of space. So next time you think about your weight, remember that it's not just about the number on the scale. It's a reflection of the gravitational pull of the Earth on your mass. And if you ever find yourself on another planet, you'll experience firsthand how this fundamental concept of physics plays out in the cosmos. Section 5. Newton's Apple, a Moment of Epiphany. The story of Isaac Newton and the falling apple is one of the most famous anecdotes in the history of science. It has been told and retold countless times, capturing the imagination of both young and old. This simple yet profound tale has become a symbol of scientific curiosity and the quest for knowledge. Whether apocryphal or not, it encapsulates a pivotal moment in our understanding of gravity. The image of Newton pondering the mysteries of the universe while observing a falling apple is etched into the collective consciousness of humanity. Legend has it that a young Newton, while sitting in his garden, was struck by the sight of an apple falling from a tree. This seemingly ordinary event, something that happens countless times every day, became the catalyst for a revolutionary idea. This seemingly mundane event sparked a profound question in his mind. If an apple falls to the ground, does the moon, high above, experience the same pull? Newton's curiosity was piqued, and he began to ponder the forces at play in the universe. This simple question led Newton down a path of inquiry that culminated in his groundbreaking law of universal gravitation. He meticulously worked through his thoughts, jotting down equations and observations, slowly piecing together the puzzle of gravity. He realized that the force responsible for pulling the apple to the ground was the same force that held the moon in orbit around the Earth. This was a monumental leap in understanding, connecting the motion of celestial bodies with everyday occurrences on Earth. The same force, he deduced, was responsible for the planets orbiting the sun. This realization unified the heavens and the earth under a single elegant principle, and indeed all objects with mass towards each other. Newton's law of universal gravitation was a profound insight that changed the way we understand the universe. Newton's apple, whether real or a product of scientific lore, illustrates the power of observation and the interconnectedness of the universe. It shows how a simple observation can lead to a deeper understanding of the fundamental forces that govern our world. It serves as a reminder that sometimes the most profound discoveries can stem from the simplest of questions. The story of Newton and the apple is a testament to the power of curiosity and the importance of asking questions, no matter how trivial they may seem. It encourages us to look at the world with wonder and to seek answers to the mysteries that surround us. In every falling apple, there is the potential for a moment of epiphany, a spark of insight that can change the course of history.